This gameplay that you're looking at right now is not me playing Balatro. Instead, I spent the last few months training an AI to play Balatro using reinforcement learning. And this video is going to cover everything I learned and how the AI ended up performing. But before we get into that, I want to get into some quick disclaimers. The first and most important disclaimer is that I've only trained the AI to play a small part of Balatro, not the whole game. If I try to train the AI to play the whole game, this project would probably take me years. And the last disclaimer is I don't want this video to be hours long, and so I will be simplifying topics as much as possible. If you want to go more in depth into a certain topic, I'll make sure to link to as many resources that helped me throughout this journey. With that out of the way, let's start with reinforcement learning, also known as RL. If you don't know what RL is, it's a branch of AI where an agent learns through trial and error. The AI takes actions in an environment and it optimizes those actions based on rewards. A simple example is to imagine an environment where the goal is to teach the AI to move a mouse towards a piece of cheese. If the AI moves this mouse closer to the cheese, then we would give it positive rewards to incentivize the AI to do more of that. If the AI moves the mouse further away from the cheese, we would give the AI negative rewards, basically punishing the AI. The idea is that through enough trial and error and clear reward signals, the AI should improve its ability to accomplish the goal that we set out for it. I've always wanted to mess around with reinforcement learning, so I figured why not teach an AI to play a game like Balatro? Balatro is a roguelike game where you play poker hands to reach a certain chip requirement. If you don't reach the chip requirement, you lose. If you do reach the chip requirement, then you get to move on to the next round. And after a few months of tinkering, I ended up creating this system. This diagram is just a simplified, high-level overview of the system. In the first part of this video, I'll walk you through all of the main pieces and how they work together to get an AI to not only play Balatro, but actually improve at Balatro. Then after that, we'll get to the fun part where I'll show you the training results. That's where I'll go over how well the AI ended up performing and how many hours the AI racked up on my Steam account. So let's start with Balatro. The first hurdle was figuring out how to control the game programmatically. I needed two things. One, I needed a way to get the current game state to feed into the AI so the AI knows what's actually going on. And two, I needed a way to execute certain actions in the game like selecting a card or clicking the play button. One of the reasons why I picked Balatro in the first place is that it has a modding community, which is where lovely-injector comes into the picture. Balatro is made using the Love2D game engine, and lovely-injector helps us inject our code into the game at runtime. This would normally be a terrible thing for competitive games, but in Balatro, this means we can modify the game however we want. But I had one rule. I could not change the game's mechanics. I wanted the AI to play Balatro as purely as possible. So the only tweaks I can make were getting the game state and triggering actions. That's it. To do that with lovely-injector, I needed to write patch files. All we had to do was write the code that we wanted to be injected, then specify where in the Balatro source code we wanted that code to run. And with that problem being solved, all that was left for me to do was to read through hundreds of lines of Balatro source code to figure out where the game state was stored, and also figure out how to trigger certain actions that the AI would eventually trigger. We now had to figure out this part, which is the reinforcement learning piece of the puzzle. That's where Stable Baselines 3 comes into the picture. SB3 is a framework that comes with reinforcement learning algorithms built in. So instead of me coding them from scratch, I can just focus on building the Balatro environment while SB3 handles the heavy lifting when it comes to training. But before we jump into SB3, we need to understand the reinforcement learning loop. And this image from Wikipedia sums it up perfectly. Let's start here with the environment. This is the AI's playground. Since we are training the AI to play Balatro, the environment in this case is obviously Balatro. The interpreter is where we take the raw information that we have extracted from the game and convert it into a language that the AI can understand. For example, the AI doesn't know what a queen of hearts is, so instead we might encode queen as the number 10 and hearts as the number 0. Don't worry if that didn't make sense, I'll expand more on this later. But from the interpretation, we get a reward and a state. A state is like a snapshot of the information in the game, like how many hands are left, how many discards are left, what cards are shown, etc. Now, when using SB3, the agent is basically a black box. This is where the RL algorithm runs. So the agent is deciding what to do, which ultimately leads to the action. This is where the agent makes up its mind and chooses the action it wants to take. In the beginning of training, these actions will be quite ridiculous, but of course, with trial and error, the RL algorithm will start to learn what actions are good and what actions are bad. This is where the reward comes in. Once the agent takes an action, this should change something in the game, right? So then we compare the new environment to the old environment, and from those two environments, we interpret a reward, just like the earlier mouse example. Now that we know more about the reinforcement learning loop, we got to go a bit deeper into SB3. The first thing I had to do was to create a custom environment. With SB3, we have to use a gymnasium interface, which gives us some methods that we have to implement for everything to work together. The two main methods being step and reset. The step method runs once per training loop, and it pretty much follows the same reinforcement learning loop I showed earlier. We receive Balatro's game state, feed it to the agent, get their action, and calculate rewards. The reset method just refreshes the environment so the agent can start start a new game after a win or loss. I'm calling it a game here, but the official terminology that SB3 uses is an episode. So an episode is just one complete run of a game. If we take Balatro, for example, from the time we press play to the point where we lose or win, that would be considered one full episode. But for the AI, I had a simple goal. One episode was going to be the first blind. Whether the agent won or lost, we'd reset. The only difference was in the rewards it got. But before we dive deeper into the SB3 environment, we have to pause and discuss this part of the diagram, or else things might not make a whole lot of sense. For the agent to train, it needs two things: to read the game state and to send actions back. But the problem is that Balatro and the SB3 environment are two separate running programs. So to connect them, we need some sort of communication medium, and there are many options. For example, we could create an API and send data through HTTP requests, which is great, but kind of overkill for our scenario. We could also use sockets, which open up a direct network connection between the two programs. This is also great, but would require a bit more setup. We could also use file IO, where we have both programs reading and writing to a file. This is simpler, but it's a bit slower since you're constantly writing to a disk. There was another option I ultimately ended up picking, which was pipes. Pipes are basically a channel of communication between two processes. One process writes data into the pipe, and the other process can read that data. In my case, I decided to create two pipes so that Balatro can communicate to SB3 from one pipe, and SB3 can communicate back to Balatro from the other pipe. The exact data going through these pipes was just JSON. The whole flow went like this. Whenever something in the game changed, we would extract the relevant information into a JSON format. Again, these are things like the cards in play, the chips, the amount of discards left, etc. Whatever is relevant to our goal. We then had a function that would send that JSON through the Balatro request pipe to the agent. After the agent makes its decision on which action to take, we convert that action into a JSON and send it back to Balatro through the Balatro response pipe. Then Balatro would read that response and execute that action in game. So now that we know how we are getting the game state from Balatro, we need to set up our observation space. An observation space just tells us what kind of data the agent will receive. We are right here in the reinforcement learning loop. But the agent doesn't speak our language or the language of our environment. It doesn't know what a queen of hearts or a flush is. What the agent really understands are numbers. Just as if you were translating English to Spanish or Japanese to Portuguese, we're basically doing the same thing here. Before we can train our agent, we have to translate our game state that we get from Balatro into numbers that the agent can actually use. But you might wonder, how do you turn things like King of Spades into numbers? But it's actually simpler than you think. For example, with suits, I decided to map them like this, meaning every single time the JSON data shows a heart, translate that to a 0, or if the data shows a diamond, translate that to a 1, and so on. You can see here another example where I translate the card's values. So every time the agent sees a jack, we translate that to a 9, and so on. The key part here is consistency. As long as we're consistent, the agent can learn patterns from it. Imagine you train the agent to see hearts as a 0, and then decide later to change the value to a 4, then you will have to retrain your agent from scratch because all of the old training data is basically useless now. The only tedious and time-consuming part is that we have to do this translation for the whole game state. This is an example of the actual game state that the agent would get. But after that's all done, all of it will get flattened into one big array like this. This is literally what the agent is seeing. Once we had the observation space set up, the next piece was the action space. If the observation space is what the agent sees, the action space is how the agent responds. If we take Pong as an example, the paddle only moves up or down, so our action space is limited to 2 moves. In Balatro though, I defined 3 main actions: select hand, play hand, and discard hand. The play hand and discard hand actions are very simple. You simply just click the play or the discard button. But select hand is trickier because the agent needs to tell us which cards it wants to pick. So knowing the problem here, I decided to split the action space into 2 parts. The first part was reserved for the action type. So if the agent returned 0, it would mean they wanted to do the select hand action, 1 would be for the play hand action, and 2 would be for the discard hand action. The second part would be reserved for the card indices. This is an array of 0s and 1s where a 1 means select this card and 0 means don't select this card. For example, let's say we are in this state and the agent wants to select the first 5 cards. It would output the action type number 0, meaning select hand, and then in the rest of the array, set the indices of the cards it wants to select to 1. So the agent would output something like this. Now that the agent has selected the cards, let's say the agent wants to play this hand. Then all it has to do is output something like this, where the 1 means click the play hand button. Now again, this is the action space in the agent's language, but I want to send this back to Balatro. So now we simply have to do the reverse process and translate the action from an array to JSON, and then send it back to Balatro through the Balatro response pipe. At this point, Balatro would receive the JSON and run the specific function that executes the action in game. Now that the agent can see the game state and take actions, the next big piece is reward signals. When we humans learn something new, we can usually figure out the goal pretty quickly because we bring in past experiences and intuition, but I had to think of the agent as a complete blank slate. How I like to think of it is like a guided missile that is trying to hit a moving target. The missile is our agent, and the target is whatever goal we have for the agent. As the agent is moving towards that target, we have to make many corrections, and those corrections are very similar to reward signals. In Balatro, it definitely took me a bunch of trial and error to figure out a reward system that worked for the goal I had set, but for my reward structure, there were two types of rewards. Positive rewards, which are the actions I want the agent to do more of, and penalties, which are actions I want the agent to avoid. Let's start with positive rewards. The main reward that I had was obviously beating the blind. If the agent beat the blind, I would give it 50 points. This was the #1 goal. I also added an efficiency bonus by incentivizing the agent to beat the blind in as little hands as possible. So if the agent beat the blind in one hand, I would give it 25 points. If it beat the blind in two hands, I would give it 15 points, etc. This is me trying to reward efficiency. Next, I wanted to reward the agent for playing good hands. Initially, I thought rewarding the agent based on the hand type made sense. For example, something like this, where if it scored a straight, get 4 points, if it scored a flush, get 5 points, etc. But then I quickly realized that this was a terrible idea, because in Balatro, we don't actually care about the hand type. For example, there are special builds where you can have a high card go absolutely ham, scoring millions of points. So instead, I changed it so that we incentivize the agent to score as many chips as possible relative to the blind requirement. This is how the reward structure looks now. Let's say the blind requirement is 300 chips. If the agent scored 300 chips in a single hand, which is 100% or more of the blind requirement, then we would give it 20 points. If the agent scored 60 chips, which is 20% of the blind requirement, then we would only give the agent 1 point. This difference makes it so that the agent will strive to play hands that score as much of the blind requirement as possible, which will hopefully lead to more blind wins, but not just blind wins, because we want consistent blind wins. Now, those were all of my positive rewards, but now we get to the negative rewards. The first penalty was obviously losing the blind. If the agent lost the blind, then we would give it -20 points. And the next penalty was actually me trying to incentivize the agent to learn how to play the game. If the agent does something wrong that you can't do in the game, then this would trigger a retry that the agent would have to respond to. The biggest example is when the agent sends Balatro how many cards they want to select. If you remember from earlier, their action space looks like this. These 8 values determine which cards the agent wants to select. But what I quickly found out is that the agent can give me an action that looks something like this, which basically means they want to select every card in their hand. But of course, we know that we can only select 5 cards per hand in Balatro. So in these cases, I added a retry counter, and I would give the agent a -0.1 penalty per retry. So it's a slight penalty to try to nudge it back to the right direction. So now the agent can see the game state, take actions, and get feedback through rewards. The last piece is, how does the agent turn all of this experience into better decisions? That's where reinforcement learning algorithms come in. The thing about learning a new game like Balatro is everyone's got a different learning process. Some people are slow and methodical, meanwhile others like to brute force it and mash buttons. You can think of that as your learning algorithm, the process your brain follows to learn something. Reinforcement learning algorithms work the same way. Once the environment is set up, we need to pick an RL algorithm to train the agent. This is why we are using SB3 in the first place, since it already includes popular algorithms, so we don't have to code them from scratch. The one algorithm I went with was called Proximal Policy Optimization, or PPO for short. Specifically, I used a modified version of PPO called Maskable PPO. There wasn't a genius reason why I picked this algorithm. The only reasons were that, first, PPO has been used to play complex games like Dota 2, so if PPO can be used to play Dota 2, I imagine that it would be capable enough to play Balatro. And second, the maskable part prevents the agent from trying invalid moves, which saves a ton of wasted training time. For example, if we look back at our action space, the agent could normally output something like 0, 1, or 2 for select cards, play hand, or discard hand. But what if the agent ran out of discards? Normally, the agent might still try to discard, which would just fail and waste training time. But with maskable PPO, I can mask out the discard hand option, which basically tells the agent that you can only select the play hand button. That way, all of its learning effort goes into mostly valid moves instead of spamming invalid moves. So now that we've gone through the full system and how all the components tie together, let's talk about training. One tool that helped me a ton was TensorBoard. TensorBoard is a visualization tool that helps us visualize how our SB3 training is doing. This gave me the ability to see a bunch of graphs, most of which I had no clue what they meant, but there was one graph that made sense to me, and that was the EP-RU mean graph. This graph shows the average reward per episode. If the average reward kept going up per run, then I knew the agent was learning, but if the graph flattened or dropped, that's when I knew I had to go back and fix something. My main goal was to get the agent to break the 50% win rate mark, meaning for a whole run, it would have to win more than half of the games. I will show in a second the win rate that I ended up reaching, which was way more than I could imagine. But first, let me go through some of the stats here so you can understand how the training sessions actually worked. What you see here is the last training block that I did. All of these rows are different training sessions. So for every session, I was able to put down the amount of steps that I wanted the agent to train for. As you can see, the agent ended up finishing in 25 training sessions. Some runs were very short. Like you can see, there is a 16,000 step run that ended up running for more than an hour. But you can see other runs that lasted for 100,000 steps or 250,000 steps. There was actually one training run that I ran for 800,000 steps. And if you're curious, this training run ran for 3.5 days. Yes, I literally left my computer on for 3.5 days while it trained in the background. Now you might be wondering about the win rate. As I said, my goal was to get the agent to have greater than a 50% win rate. To track the win rate, I just added some logs that calculated the win percentage for the whole training run. Honestly, in hindsight, I probably could have used TensorBoard to record this data and have it look pretty on a graph, but it's a little too late for that now. But did I beat my goal? Was the agent able to get more than a 50% win rate? Yes, the training was a success. Not only did it beat the 50% win rate goal, but I kept training it just to see how high it would go, and the highest win rate I got to was 78%. Honestly, I thought hitting a 50% win rate was going to be impossible, especially since this was my first time using reinforcement learning, but the agent ended up doing really well. You also have to understand too that this was the successful training block. I had a bunch of other training blocks that did not go well at all, either due to bugs that I had to fix or reward signals that weren't good enough. And if we take all the time that we see in TensorBoard here and add it up, it looks like the final training block here took almost 18 days of training. Part of the reason why this project took so long is, of course, I had to build out the system here, but also because it takes time to train the agent. So imagine spending a week training an agent just to realize there's some bug that I missed or that there's some improvements that I need to make. Most of the time, that meant I needed to restart training from scratch. But of course, it's all part of the process. Not only am I trying to train the agent, but also, being that this is my first time doing this, I'm also trying to train myself. Also, as a side note, I started off this project with roughly 70 hours in the game on Steam. This was 70 real hours of me playing the game and having fun. This was not RL related, but by the end of the project, I had 708 total hours in the game. That's a total of 630-ish hours of development and training time. Most of it from the game running continuously for days on end. Now, I want to finish off the video with a final treat because I haven't mentioned this yet, but I actually built a replay system. Now, it's not a sophisticated replay system, but basically it saved the top 10 runs that the agent did throughout these 18 days of training. I have these runs inside of this replay.json file, which I haven't opened yet because I want to show my live reaction. So let's open it now and see the best run that the agent did. There's a replays.json file, and I have not looked at this at all. For context, right? When you do a new run, right? This is the deck that the agent was playing on. And when you do a new run, naturally the first blind, you need to score at least 300 chips. Every single run was ran on that, right? And so this replays.json, we're gonna see what the top run was. We're not gonna go through every one of them, but let's go. What? How is that possible? It basically saved the actions, the seed, so that I can replay it in the date and time, and the highest score was 1,480, which I genuinely don't know how the agent got this high. What is the second top? Oh, 1,407. Okay, so not that far off. By the way, I don't know if you've noticed, but this is sorted in order. Let's show this on VS Code actually. Replays.json file. So it looks like the top episodes for this agent was clocking in around this number. That's insane to me. So we're gonna play it out and we're gonna see exactly how did they end up scoring this, because I genuinely don't know how they did that. So this is the seed. Do a new run, do seeded run, and we're gonna enter the seed. And then let's paste seed. So yep, K6, all that stuff. Cool, so let's now play it. So this is the seed. And of course the agent selected this. Okay, so we already see like a full house. So let's see, what does the agent do in this scenario? So the agent does action 1. Let me refresh myself on what action 1 is. So it looks like number 1 is select hand, and number 2 is play, number 3 is discard. So if you notice in our replays.json file, all we did was save the seed and the actions. We can essentially figure out what they scored by just going into the seed and then following the exact same actions that they did. So it looks like they did in action 1. So they picked 4, 5, 6, 7, 8. So they decided to do 4, 5, 6, 7, 8. So that's a select hand. So they did that. Then they did action 2, which is play. So they played this. Okay. Then they did action 1, which is select, of course. So 1, 2, 3, 4, 5. So they did 1, 2, 3, 3, 4, 5. And this was a pair. So they ended up getting that because they played it with 2. Then they went 4, 5, 6, 7, 8. 4, 5, 6, 6, 7, 8. And then they played that, which should win, no? Wait, it didn't win. Oh. Okay, and then the last move that they went for was a 1, 2, 3, 4, 5. And as you can see, that's a royal flush. And that netted the 1,480. Wow. Holy crap. This agent went crazy. Okay, let's do one more. It seems like maybe the royal flush is the thing that like gets you over that hump. Let's do one more and see how they got. It looks like they got how much? They got 1,471 here. So they did a 4, 5, 6, 7, 8 in this scenario, right? So let's see. So 4, 5, 6, 7, 8. What do they do with that? So they decided to discard these cards. And then they did a 4, 5, 6, 7, 8 again. Interesting. And then they decided to discard again. Okay. They're looking for cards that are in the high end, it looks like, because they keep discarding the low end. And then they do a 4, 5, 6, 7, 8 again. So 4, 5, 6, 7, 8. Or, you know, I did that backwards. Anyways. They decided to discard again. So it seems like the agent looks to be fishing. It seems to be like discarding low-end cards and like fishing for something, to hit something, right? And so now they do it, they pick these cards. So they pick 2, 4, 5, 6, 7, 8. So this is 6 cards. And so this would have resulted in a retry. So the agent kind of failed. Same here, 3, 4, 5, 6, 7, 8. This is 6 cards. It would result in a retry. And then it just decided, okay, 4, 5, 6, 7, 8 again. Okay, so 4, 5, 6, 7, 8, right? And then it decided to discard. Okay, so discard. So at this point, right, we have 0 discards and we still haven't scored anything. So the agent says, okay, let's do 3, 4, 5, 6, 7, 8 again. Too many cards, so we have to retry. 3, 4, 5, 6, 7, 8. They tried it again, realized they can't play that. 4, 5, 6, 7, 8 again, which is interesting. And then they go for a play. So this is just a pair of 10s. They do a play there, great. Again, they pick too many cards, so 6 cards won't work. Then they try 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5. So they end up hitting a 3 of a kind. Pretty good. Doesn't get you over the threshold, but it gets you close. So now we try 2, 4, 5, 6, 7, 8. Again, too many cards, too many cards. And then we try 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, which isn't really anything. It's just a high card, which is not going to get us to that threshold. And look at that. It looks like another royal flush is about to happen. So now we do a 1, 2, 3, 4, 5. So the agent sees this, and then of course, if we look at the replays.json, they play it. So boom, royal flush. Gets us up here. So it seems like there's like a common trend, because if you really think about it, like you don't have any jokers, you don't have any like special cards. The only way you can get a high scoring, run is to score a high scoring hand. But it seems like for the top scoring plays, all it was really doing was discarding low, discarding low, discarding low, and then like kind of playing low until it got kind of lucky, right? Because these are the top 10 runs out of like probably thousands and thousands of runs, right? So it probably ended up getting pretty lucky and ending up with a royal flush, which ended up getting them near 1,500 score, right? So yeah, I mean, I'm so happy to see, like get a first eye view into how this agent was kind of thinking. Honestly, never even knew you could score this high on the first blind. Normally, people would end up just trying to reach 300, right? Since that's the blind requirement there. But yeah, this is very eye-opening. This is very cool. And yeah, I hope you guys enjoyed that replay review, I guess. Yeah. Anyways, that was the journey of me training an AI to play Balatro. If you guys learned something, please hit that like button and I will see you guys in the next one. Peace.